Entropy is disorder. Systems tend toward chaos. Things deteriorate because the universe prefers disorganization. You've probably heard this before. Textbooks say it. Popular science videos repeat it. Half the physics presentations out there hammer it home. And it's wrong. Not completely. But wrong enough that for decades it's kept people from understanding why Richard Feynman, Nobel laureate in physics in 1965, one of the most brilliant minds in 20th century science, said entropy was the most important discovery in the entire history of science. Not relativity, not quantum mechanics, entropy. It's not an opinion. It's not pessimism. It's pure physics. Einstein's relativity rewrote space and time. Quantum mechanics showed us that reality is probabilistic, not deterministic. These are the two most verified, most precise, most transformative theories we have. And Feynman said entropy was more important than both. Why? Because entropy is the only law in all of physics that distinguishes past from future. It's the only law that points. All fundamental physics, gravity, electromagnetism, nuclear forces, quantum mechanics, works equally well in either direction. Record two particles interacting and play it backward. Nothing looks wrong. These laws are blind to time's direction. The second law of thermodynamics is not. And if the second law creates time's direction, it explains way more than just physical processes. It explains why you have memories. Why causes come before effects. Why yesterday differs from tomorrow. And why that difference will, at some inconceivable moment, cease to exist. Feynman called this science's most important fact because he saw entropy wasn't just a thermodynamics detail. It's the law that governs existence itself. It's what makes the present possible and the future inevitable. What did he see in entropy that most people missed? That is the central question. And to get there, you first need to understand why the definition, disorder, isn't what physics actually says. The most popular definition, disorder. Systems tend toward chaos. Things deteriorate. The universe prefers disorganization. There's some truth here. But it's an oversimplification that sabotages real understanding. The problem? Disorder is subjective. Disordered to whom? A scattered pile of bricks looks messy to an architect. But physics doesn't care about aesthetics. Physics doesn't know what tidy means. It operates with microscopic states, not human concepts of beauty or organization. Boltzmann replaced the metaphor with math. Picture a closed box with gas inside, say, 1,000 nitrogen molecules. Each has a position and velocity at any moment. Every specific combination of positions and velocities is a microstate. There's an unimaginably large number of them. But when you look at the box from outside, you can't see individual molecules. You measure collective properties, temperature, pressure, volume. That's the macrostate. Boltzmann's question was simple. How many different microstates produce the same macrostate? That question defines entropy perfectly. Boltzmann put it in an equation now carved on his tomb in Vienna. S chart K log W. S is entropy. K is the Boltzmann constant 1.38 times 10^23 joules per Kelvin. W is how many microstates match the observed macrostate. So entropy isn't disorder. It's how many different ways a system can be configured internally and still look identical from outside. Here's a concrete example. Take a deck of cards. Perfect order ace to king, suit by suit is exactly one sequence. Just one microstate matches perfect order. A shuffled deck? That's about 8 kicks 1067 possible sequences, 80 followed by 66 zeros. Nearly all of them look shuffled. When you shuffle, it doesn't fall into chaos because nature likes disorder. It falls into chaos because there are vastly more shuffled states than ordered ones. Pure statistics. You move toward whichever state has more ways to exist. This changes everything. The air you're breathing is spread throughout the room, not packed in one corner. Not because the universe prefers that, but because there are far more microstates with air spread out than crammed together. Technically, nothing forbids all the molecules from spontaneously concentrating in one corner and suffocating you. It wouldn't break any laws. The probability's just so close to zero that it'll never happen is basically equivalent to impossible. Now here's what Boltzmann saw clearly, but it took physics decades to accept it. The order we see in the universe isn't an anomaly or a separate law. It's just a state of extremely low probability. The universe started in an extraordinarily improbable state, far more ordered than random chance would suggest. And since then, it's moved toward more probable states, as statistics demands. If order is improbable and the universe started with extraordinary order, then the real question isn't why do things deteriorate? It's why did the universe start so improbably? Where'd that initial order come from? Feynman said this is one of science's deepest questions. But it only makes sense once you understand why the law governing all this occupies a unique place in physics, unlike anything else. Clausius formalized the second law around 1850. Simple version. In an isolated system, total entropy never decreases. It can stay constant in perfectly ideal, reversible processes, isentropic ones, but any real process increases it. In 1865, Clausius named it entropy, from the Greek tropos, transformation. And that word? It names the process that dooms everything. Here's a simple fact. Heat flows from hot to cold. Always. Never backwards. Seems obvious. But Lord Kelvin saw something devastating hidden here. Energy degrades. Organized energy that can do work transforms into scattered thermal energy that can't be recovered efficiently. And unlike almost everything else in physics, this process is irreversible. Why is this law different? Why do physicists revere it more than relativity or quantum mechanics? Arthur Eddington said it best. The British astrophysicist who proved Einstein right during the 1919 eclipse stated, "If a theory contradicts observations, the observations might be wrong. If it contradicts Maxwell's equations, they can be refined. But if it contradicts the second law, there's no hope. The theory collapses in shame." He wasn't being dramatic. He was being precise. What makes the second law fundamentally different? Time symmetry. Newton's laws film gravity in action and reverse it. The physics still works. Maxwell's equations for electromagnetism? Reversible. Schrödinger's quantum equation? Time symmetric. General relativity? Time symmetric. All fundamental laws work the same forwards or backwards. We call this symmetry under time reversal. The second law isn't like that. It distinguishes. It points. Past, low entropy. Future, high entropy. And that distinction, Feynman argued, is what creates past and future themselves. Boltzmann turned all this into rigorous statistics. And what happened to him because of it? One of science's most disturbing stories. The scientific community wasn't ready for nature being fundamentally probabilistic. Classical physics was deterministic given starting conditions. The future was fixed. That the second law was probability, not absolute necessity. Too philosophical, almost heretical. Boltzmann spent decades in vicious debates, often isolated academically. In 1906, at 62, he took his own life while on vacation with his family in Trieste, Italy. The tragedy? He died without knowing he was right. Years later, experiments overwhelmingly confirmed matter's statistical nature and his theory's validity. S. Moore's K log W was carved on his tomb in Vienna. Belated recognition for a mind science didn't know how to handle. But Boltzmann left an open question that haunted him. If every microscopic law is perfectly reversible, where does macroscopic irreversibility come from? Where's the arrow of time? This arrow points somewhere specific. And understanding where it points is what will make Feynman's contribution, the one that's been implicit from the start, completely clear. Where's entropy taking the universe? Heat death. And it's nothing like what people imagine when they picture the end. It's not an explosion, not gravitational collapse, not fire or ice in any dramatic sense. It's something far stranger and more definitive than any catastrophe you can picture. Perfect silence. To understand what this means, you need to know what allows any process to happen. For any process nuclear fusion in a star, thought in your brain, there's gotta be a difference. Higher temperature here, lower there. Energy concentrated at one point but not another. That's a gradient. Watch coffee cool on a table. Heat flowing from coffee to air. That's a gradient being consumed. Battery discharging. Muscle contracting. Cell dividing. All gradients consumed. Gradients make things happen. Temperature difference. Heat flows. Chemical concentration difference. Molecules diffuse. Electrical potential difference. Current flows. Every physical transformation, chemical reaction, biological process Every phenomenon you've ever seen in nature happens because a gradient's there to be consumed. Maximum entropy, all gradients completely gone. Temperature uniformly distributed everywhere, no hot or cold regions, no energy concentrations. Every particle in thermal equilibrium with every other. No stars, they're regions of extreme temperature relative to space. No chemical reactions, no light, no energy transformations. And we'll get precise about this in a moment. No time in the sense that time flows forward. Because time's flow is linked to entropy increasing. And at maximum entropy, nothing changes. Without change, there's no way to distinguish before from after. It's called heat death because of thermal equilibrium. But it won't be hot. It'll be extremely cold temperature near absolute zero, distributed uniformly across a universe massively dilated by accelerated expansion. How long? The universe is 13,800,000,000 years old now. Models estimate complete heat death around 10,100 years, a 1 followed by 100 zeros. Perspective. The last supermassive black hole evaporates via Hawking radiation on the same timescale. After that, the universe is a rarefied cloud of ultra-low energy photons, electrons, positrons, and neutrinos spreading forever through increasingly vast space. Here's the precise detail that justifies the title. Entropy doesn't reach maximum all at once. It approaches asymptotically, like a curve approaching a horizontal line without touching it. You can get infinitely close, but never reach it. No overshoot, no reversal, no spontaneous second cycle starting from maximum. The universe approaches a limit that defines what it can fundamentally be. But Feynman became obsessed with something else. Heat death isn't the most disturbing part. The disturbing part is what it implies about right now, about the nature of time you're experiencing. In 1961, Feynman started lectures at Caltech that became the Feynman Lectures on Physics, maybe the most cited physics lectures ever. During thermodynamics, he made a statement that sounds simple until you really think about it. He said, "If you want to know why the past differs from the future, the only answer physics offers is the second law." Think about that. You're reading this now with memories of yesterday, not tomorrow. Causes come before effects. Eggs break, they don't reassemble. Smoke rises and disperses, never reconcentrates and falls back down the chimney. Obvious stuff. So obvious it seems to need no explanation. But physics equations don't know this. Microscopic physics is blind to direction. Its equations describe a universe where past and future are mathematically identical. Film an electron with an electromagnetic field and play it backwards. A physicist can't tell which direction is forward. So Feynman's question is simple. Where does this asymmetry come from? His answer: it doesn't come from microscopic laws. It comes from the universe's initial state. We live in a universe that started with extremely low entropy. The Big Bang was a highly ordered, concentrated energy configuration, astronomically improbable. Since then, the universe has moved toward more probable states, as the second law demands. That movement from low to high entropy is what we call time flowing forward. A broken egg doesn't reassemble because the intact state has far fewer possible microstates than the broken state. For reassembly, molecules have to coordinate movements in one specific, extremely unlikely way. Physics doesn't forbid it. It's just statistically impossible for any practical purpose. Memory works because information-storing processes are thermodynamically irreversible. Causality exists because entropy increase guarantees lower entropy comes before higher entropy, which defines time's direction. For Feynman, time isn't a separate dimension flowing independently. It's the macroscopic expression of living in a universe far from thermodynamic equilibrium. Here's the deepest question Feynman identified, one of physics' great open problems. If time's arrow comes from the universe starting with extremely low entropy, why'd it start that way? This question is fundamentally disturbing. The second law says entropy never decreases in an isolated system. But it doesn't explain why the universe started ordered. It describes what happens from initial conditions. It doesn't explain the initial conditions. The Big Bang's low entropy is extremely improbable. In a random universe, the probability of our ordered start is inconceivably small, more zeros than particles in the observable universe. Feynman and physicists like Penrose called this cosmology's deepest mystery. Why didn't the universe start in equilibrium? Was something before the Big Bang that set this? Is there a deeper law explaining initial low entropy? Current physics has no answer. Speculations? Yes. Hypotheses? Yes. But no verified theory explaining why the universe began improbably enough for time to exist. Then Feynman found something that seemed completely unconnected, but turned out to be the same problem in different language. In 1867, Maxwell, the physicist who unified electricity, magnetism, and light, published a thought experiment, Maxwell's demon. It's elegant and seemingly devastating to the second law. Picture a box divided by a wall with a small hole. A tiny creature, the demon, controls it. Gas molecules move randomly on both sides with varying speeds. The demon watches each molecule. Fast one from the right, opens the hole, lets it through left. Slow one from the left, lets it go right. Over time, the left accumulates fast molecules, higher temperature, and the right accumulates slow ones, lower temperature. Without spending energy, the demon created a temperature difference from nothing. It seems to have reversed entropy increase, turning an equilibrium system into two unequal systems. If the demon works, the second law fails. Physicists debated this for almost 90 years. In 1929, Brillouin showed the demon needs to measure each molecule to know if it's fast or slow, and measurement costs energy. But then came a challenge. What if the demon had passive photoreceptors that used no energy? The real answer came in 1961 when Landauer showed something that completely transformed how we understand physics and information. The demon processes information about each molecule. Every observation creates an information bit in the demon's memory. But memory's finite, so eventually it has to erase old information to keep operating. And Landauer proved something radical. Erasing information, not storing it, processing it, just erasing it, dissipates energy into the environment. Every erased bit produces at least kT-ln2 heat, where K is Boltzmann's constant and T is temperature. That's Landauer's principle. And the implication is fundamental. Information is physical, not abstract. Destroying every bit costs real thermodynamic energy. Here's a bizarre coincidence. While Landauer solved Maxwell's demon in 1961, an American engineer had reached the same conclusion 13 years earlier from a totally different field. This engineer was Claude Shannon. In 1948, he developed the mathematical theory of communication, how to measure information in a message, calculate transmission channel capacity. Practical goal: telecommunications. Nothing else. Shannon wasn't thinking thermodynamics, but his formula? Mathematically identical to Boltzmann's entropy formula, not similar. Identical. Same mathematical structure, discovered independently, completely different field, 70 years apart. Shannon called it information entropy. Not a naming coincidence. It's structural. Thermodynamic entropy and information entropy are the exact same thing in different contexts. Boltzmann measured uncertainty about a physical system's microstate. How many molecular configurations produce the same observable state? Shannon measured uncertainty about a message's content. How many symbols match what you already know? The math is identical because the problem structure is identical. Feynman articulated this connection most clearly. To him, the universe's heat death wasn't just the end of processes. It was complete information erasure. Every structure, pattern, configuration that emerged in 13,800,000,000 years of cosmic evolution will be gradually destroyed as entropy approaches maximum. The universe doesn't just stop existing as a structure. It loses the memory of everything that ever was. This entropy-information connection explains something paradoxical. What happens to information in a black hole? In 1972, Bekenstein was a doctoral student with Hawking. At that time, Hawking said black holes had no entropy, simple objects, described by three parameters: mass, charge, rotation. Bekenstein disagreed, with precise physical reasoning. Take a highly organized object, a library of books with massive structured information, and throw it into a black hole. What happens to the universe's entropy? The library vanishes behind the event horizon. All that organized information disappears. If the black hole has no entropy, the universe's total entropy apparently decreased, violating the second law. To avoid violating the second law, the black hole must have entropy. Bekenstein calculated what it'd need to be. The answer? Surprising. A black hole's entropy is proportional to its event horizon's area, the spherical surface beyond which light can't escape, not its volume. Deeply counterintuitive. In other physical systems, entropy grows with volume, more space, more microstates, more entropy. Black holes? The area is what matters. Hawking, initially skeptical, mathematically confirmed Bekenstein and discovered more. Black holes emit thermal radiation. That means they're not eternal. They slowly lose mass and eventually evaporate. A supermassive black hole evaporates around 10–100 years far away, but finite. The consequence is monumental. Black holes are the highest entropy objects in the universe. One supermassive black hole at a galaxy's center has more entropy than all observable content around it. They're closer to the entropic limit than any other structure. Here's where it gets dizzying. Bekenstein and others realized the principal entropy proportional to area, not volume, might be universal. They developed the holographic principle. The maximum entropy or information in any space region is proportional not to its volume, but to its surface area. The universe might fundamentally be surface reality we project as three-dimensional. The holographic principle is one of theoretical physics' most radical ideas, emerging directly from Bekenstein's black hole physics. The final black hole evaporation will likely be the last major thermodynamic event before heat death. After that, the universe is an ultra-rarefied cloud of structureless particles expanding forever in perfect equilibrium. At the extreme limit of this scenario is something called a Boltzmann brane. In a universe with enough time far beyond 10–100 years, random statistical fluctuations could spontaneously generate complex structures. A conscious observer emerging from thermodynamic void by pure probability. The probability is so insanely small, it needs timescales making 10–100 years look instant. Physics doesn't formally forbid it, and some cosmologists say Boltzmann branes in infinite-time cosmologies pose serious problems for eternal universe models. So here's the implicit question from the start. Is there any way out? Seems natural after what we've seen. Life reduces entropy locally. Intelligence organizes. Civilizations build. Maybe on a large enough scale with advanced tech you could push back. Physics says no. Understanding why is central to what Feynman saw as the most profound point here. Life, intelligence, and all organized structure don't escape the second law, they execute it. When you metabolize food, you reduce entropy in your body locally, but you dissipate more heat, produce more waste, and increase environmental entropy more than your local reduction. Total balance? Always positive. Living organisms are thermodynamic machines that process energy gradients, extract work, and produce more residual entropy than their structure suggests. A technologically advanced civilization isn't a solution to the entropic trend. It's a more efficient way to fuel it. More complex organization means more intense entropy production supporting it. Penrose proposed conformal cyclic cosmology. His idea, a heat-death universe empty, extremely cold, just massless particles like photons, is mathematically equivalent to a Big Bang for the next cosmological era. Without massive particles, distance has no defined scale, and space becomes topologically resettable. Penrose calls them eons. Elegant idea. But it's speculative, unverified experimentally, with serious questions about what continuity means between aeons with no transferable memory. No known physics framework reverses increasing entropy in an isolated system. Not a technology limit. A structural limit of what the universe fundamentally is. So the implicit question from the start has a simple, definitive answer. There's no way out. The universe is heading toward heat death. No exceptions, not for life, not for intelligence, not for any imaginable civilization. Feynman, being Feynman, didn't see this as a reason for despair. He saw it as the most enlightening fact about reality. The entropic limit isn't a flaw. It's what makes the universe comprehensible. No second law. Time has no direction. No time direction. No memory. No memory. No causality. No causality. No physics. No story. No meaningful existence. The entropic limit isn't approaching like a catastrophe. It's the silent backdrop where everything's already happened. Every star formed, every organic molecule organized, every thought ever crossed a cosmic mind. Feynman said, understanding this changes how you see right now. Not with fear, with precision. The order you observe around you. Any scale, atom to galaxy, is statistically improbable, thermodynamically temporary, physically precious. Not because it lasts forever, because it exists at all. The low-entropy state we inhabit, 13,800,000,000 years after the Big Bang, still with active stars, still with energy gradients sustaining complex processes, still far from equilibrium, is the thermodynamic window, making structures like brains capable of perceiving this window possible. Low entropy isn't just good for life. It's the necessary condition for anything wondering about the universe to exist. But there's one last question, the most baffling. If the universe needed extremely low entropy to start for time to exist, for memory to happen, for you to be here asking this, why do the physical constants seem tuned with surgical precision exactly for this? That's the anthropic principle, and that's the next video.